bright and early on the West Coast. East Coast got to sleep in a little bit. Good to see everyone this morning. All right, and I believe Sarah Gibbons is here as well this morning. Sarah, where are you?
Here's me. Good morning.
Good morning. So Sarah is going to be monitoring the chat this morning. So if you have any questions, feel free to put those in the chat, and she will do her best to answer. And if we come into any problems, we'll answer them at the end. All right, it is the top of the hour. I still have some people joining, and I'm so glad that you guys came back. Yesterday was kind of rough. It's a long day. Long day. All right. Almost up to 100 people. It's so exciting. Okay, so what are we going to do today? We have a lot to do today, and I'm going to try and keep the energy up. It has been storming here all morning. I woke up this morning really nervous about potentially losing electricity. I believe the worst is over, though, so I think we're okay. Don't want to tempt fate, but we'll see. But we're going to have a good time this morning. So what are we going to do? This is on Eastern time. So do the math based on your own time zone. We're going to start this morning with about a half an hour of physics and instrumentation. So we're going to do the tough stuff up front. And then we're going to do just about 15 minutes of radiation safety, focusing on just those things that you absolutely need to know for your board exam. Then we're going to hit about a half an hour looking at radiopharmacy, looking at how radiopharmaceuticals are made, where they go, those kinds of things. And then that'll take us to our first break. So we're going to take breaks today because 4 hours is a long time to keep going without stopping. So we will be taking breaks. So we'll take our first break. When we come back, we're going to spend an hour on clinical procedures. That's the bulk of your exams. We're going to take an entire hour and focus on clinical procedures. And then we're going to do about 15 minutes of what I call math rapid fire. We're going to do some problems. I'm going to show you a couple of shortcuts. We're only going to spend about 15 minutes. I do have a 2-hour math review that's coming up, I believe, on Thursday this week. If math is something you're struggling in, you might want to consider doing that. And if that doesn't work in your schedule, I have another one coming up a couple weeks later. So math is very important. Then we're going to take our second break. And then finally, we're going to end with our fun Kahoot game. And when we play the Kahoot game and you log in, you do not have to use your real name. Okay, so you can play totally anonymously and just have a good time with it. All right, without further ado, we are going to jump in, and we are starting, of course, with physics. We always start with physics. All right, so we need to know what is in the nucleus. That is like the very basic thing, is what is actually in the nucleus. In the nucleus, of course, is protons and neutrons. Protons are positive, neutrons are neutral, which means your nucleus is always going to be positive. The electrons are outside of the nucleus, and the electrons are negative. Now, the protons and the neutrons are really close to being the same size, but they are not the same size. The neutron is a little bit bigger than the proton, and you can think of it as the neutron equals a proton plus an electron. And that would imply that the neutron is just a little bit bigger than the proton, which it is. All right, nuclide nomenclature. We're going to talk about families of nuclides. But before we do that, we need to talk about the element itself and how we denote the element. So if this is the symbol, this is the element itself, Z is going to be the atomic number. This is the number of protons, and the number of protons defines the element. So all isotopes of iodine will all have 53 protons, because the number of protons defines the element. So we don't need to put that number there, because we can always look that up in a periodic table. A is the mass number. This is the number of protons plus neutrons. Now this symbol, this element, will always have the same number of protons, but it's going to have different number of neutrons, and the different numbers of neutrons is what is going to make it unstable or stable. So, nuclide nomenclature. Isotopes. Isotopes, there's a P in it, same number of protons. I can easily know these are isotopes simply because they are all iodine. Gallium-67 and gallium-68, those are isotopes because they're both gallium. They have the same number of protons. Isotones. Isotones are totally useless. They really are. I mean, we learn basically the definition. They're the same number of neutrons, so I can subtract this. 130 minus 52 is 78. 131 minus 53 is 78. They have the same number of neutrons, but really isotones are totally useless. They have the same number of neutrons. It's a nice test question, but useless. Now, isobars, that's the important thing. Isobars have the same number. So, O18, F18, same number, they're isobars. Same number of protons plus neutrons, which, by the way, protons and neutrons collectively are called nucleons. I love that word. I think it's a great word. So, isobars decay to each other through isobaric transition. So what you see here is F18 decays to O18 through positron decay. Positron decay is a type of isobaric transition. Molybdenum-99 decays to Tec-99m through isobaric transition. This is beta negative decay. So isobars have the same number of nucleons. Now, if we were to plot all of the different elements and all of their different number of protons and neutrons, putting the number of neutrons on the x-axis, the number of protons on the y-axis, this straight line here is where the number of protons equal the number of neutrons, but that is not the line of stability. The blue are the stable isotopes. And all of the green, which you see some above the line of stability and some below the line of stability, all of those are radioactive. They're unstable, and their whole purpose in life is to get to the line of stability. How do they do that? Through decay. So the ones above the line of stability are going to have too many protons. A proton turns into a neutron. And we learned yesterday I need to keep both sides equal, so I need something positive, a beta positive. The alternative is a proton plus an electron through electron capture will turn into a neutron. That's electron capture. So above the line of stability, positron decay, electron capture. Below the line of stability, now I have too many neutrons. So my number of neutrons are going to turn into protons. I have to make sure that my sides equal out, so I need a beta negative particle. And this is going to keep happening. The green ones will keep doing this until they get to the blue line. All right, we saw this yesterday. Alpha decay gives off a helium nucleus. Not a helium atom, because a helium atom has electrons, a helium nucleus. Beta minus decay, neutron turns into a proton and a beta minus. Beta positive, proton turns into a neutron and a beta positive in electron capture. Proton plus electron equals a neutron. And then finally gamma emission, which this here is the result of something else that has happened. And it leaves the nucleus a little bit unstable. It gives off that gamma ray and then it becomes stable. Now these are all of our different decay schemes. And you can think of decay schemes as being on a graph. So your x-axis is going to be the number of protons and your y-axis is energy. Now you notice each one of these have a parent and a daughter, and the parent is always higher than the daughter because the parent is decaying to the daughter. So we're always losing energy because all of the arrows go downward. Now, if the arrow goes downward to the right, I'm gaining a proton, which is what happens with beta minus decay. And if it goes down to the left, I'm losing a proton, which is what happens with beta positive and electron capture. And I also lose 2 protons with alpha decay. And if my line goes straight down, like it does here, that is gamma emission or internal conversion. So we can write these out. Alpha particles have 223 nucleons, or radium. Radium has 223 nucleons. It has 88 protons. It's going to decay. It's going to lose 4 nucleons, so a mass number becomes 219. It's going to lose 2 protons, so my 88 becomes 86. If I look up 86 in the periodic table, it is radon. All right, beta minus decay. Now we have Moly-99. Moly-99 has 42 protons. We know it decays by beta negative emission. And since it's beta negative emission, which is isobaric transition, we know that this number is going to stay the same. And it's going to decay to technetium. My 42 is going to go up by 1 because a neutron turns into a proton. So my 42 becomes 43. I look up 43 in the periodic table. It is technetium. And then beta positive decay. You have rubidium-82. Rubidium-82 has 37 protons. know in beta positive decay, we're going to lose a proton because a proton turns into a neutron. So my 37 is going to become 36. Isobaric transition, so my 82 stays the same. And it decays into krypton. If I looked up 36 in the periodic table, it would say krypton. And then electron capture. Let's look at I-123. I-123 has 53 protons. Since it's isobaric transition, that 123 stays the same. The 53 is going to go down by 1, so it becomes 52. I look up 52 in the periodic table, and it is tellurium. And then, of course, isomeric transition. Isomeric transition is you just have extra energy in the nucleus. It's given off as a gamma ray, which is what happens with technetium. But now, what is internal conversion? Sometimes we hear that term too. Isomeric transition, internal conversion. Internal conversion is like when your teenager gets mad, and instead of just leaving the house, on her way out, she slams the door. And so internal conversion is when the photon is leaving and on the way out kicks one of its own electrons out. It's internally converting its own energy to itself. That's what internal conversion is. Kicks out one of its own electrons. That only happens about 10% of the time with technetium. You have to understand that the electron cloud is almost entirely space. All of the mass is huddled together in that nucleus. I mean, we write it like these electrons are real big. They're not. And so the probability of hitting an electron on the way out is very, very low. But that's what internal conversion is. All right, interactions of radiation with matter. So now we know how everything decays. We've got alpha, we've got beta, we've got gamma, we've got electron capture. Now what happens when that interacts with the matter? And the matter that we're talking about is us, patients, cameras. What does the radiation do inside of all these different things? So we have particulate radiation that's going to interact in a certain way, and then we have photons that are going to interact in a different way. So we have to treat these two separately. So our particulate radiation, alpha and beta, they have a charge. Alpha's +2, beta's going to be +1 or -1. They have mass, which means they're either going to attract or repel electrons as they move through space. Now, why is that important? Because when they attract or repel electrons, they remove those electrons, which is called ionization. That's why we're ionizing radiation, because our radiation has enough energy to remove electrons. All right, let's talk about beta negative, and then we're going to talk about beta positive. So beta negative, the interaction that we're concerned about with beta negative is if that beta negative particle comes close to the nucleus, it's going to be attracted to the nucleus. Remember, the nucleus is always positive. Beta negative is going to be attracted to the nucleus. So it's going to come close to that nucleus. And as it does, it doesn't want to go away, so it spins around and it changes directions. Now, when you're driving down the road, whoever your navigator is sitting next to you, and all of a sudden says, "Stop, turn here." And it's a tight corner, you have to slam on the brakes in order to make that turn. And when you slam on the brakes, you lose energy. And that's what's happening here, is we're losing energy. Now, if it's not a tight corner and you're further away and you're just kind of going like this, you can just kind of tap the brake. You don't lose as much energy. So you just a low energy photon. That is called a Bremsstrahlung X-ray. Now ask yourself, does beta positive produce Bremsstrahlung? Does beta positive do it? It does. We don't learn it. We don't talk about it. So beta positive, what it's going to do though is as it gets close to the nucleus, it's going to be repelled away. And it gives off that photon. Now, the reason we don't talk about it is because beta positive is going to do something entirely different. It's going to undergo annihilation. And when it does that, it's going to give off these big 511 keV photons that are going to totally overwhelm those Bremsstrahlung photons. So beta positive, positron leaves the nucleus, travels a certain distance, hooks up with an electron, annihilation, 2 photons go off in opposite directions at 511 keV. Now, how do photons interact with matter? Photons don't have charge, they don't have mass, they only have energy, and because that, they go very far, because there's nothing to stop them. So there's a couple different interactions, and I know this is very busy. I need to look ahead, what's going on, I've got a blank slide, interesting, okay. All right, this is very busy, but I'm gonna simplify this for you. There's only 3 interactions that you really need to know. One is no interaction at all, which is something that happens very often, especially in us, because we are considered high Z material. Sorry, we are considered low Z material. Low Z material, what does that mean? That means we don't have a lot of protons. And since we don't have a lot of protons, we don't have a lot of mass. And so there's not gonna be a whole lot of interaction in our bodies with photons. It's gonna go right through us. So no interaction is a very common interaction. Now, the other 2 that you need to know is photoelectric effect and Compton scattering. C, just ignore that. So, photoelectric effect is absorption, Compton scattering is scattering. Both of these are the same thing in terms of what's coming in. A photon is coming in. The difference is in photoelectric effect, we're hitting an inner shell electron, and in Compton scatter, we're hitting an outer shell electron. Now, why does that matter? The electrons are going to be attracted to the nucleus because the nucleus is positive. And the closer they are to the nucleus, the more attraction, the more tightly they're bound. And so if the photon hits an inner shell electron, it takes every bit of its energy to knock it out. There's nothing left over. And so that's why the electron is kicked out, photon in, electron out. Whereas Compton scatter, this electron is outer shell, it's really far away, it's barely holding on for dear life. That photon comes in just like, flick, it's gone. Then I didn't have to use any energy at all. So I have energy left over, which is my scattered photon. All right, that brings us to instrumentation. We have a lot of different instruments. It can be broken into radiation detectors or radiation producing. X-ray, CT, fluoro, mammo, those are machines that produce radiation. They produce radiation. Now, our radiation detectors can be broken into non-imaging or imaging. We're going to start with the non-imaging, all of these, then we're going to get into the imaging. So non-imaging can be broken into gas-filled detectors or scintillators. The gas-filled detectors, we have our GM meter, that's filled with gas, dose calibrator, which is an ionization chamber. I remember my first day in clinic it was a university hospital. And I was scared to death because as a student, you're scared to death anyways. You go into a brand new hospital, it's a big hospital. This physician there has a reputation of being really hard. And I walked in and he pointed to the dose calibrator. He said, "What is this?" I said, "It's a dose calibrator." He said, "No, what is it?" And he was really mean. And I was like, "I don't know." And he said, "It's an ionization chamber." I never forgot that. That is an ionization chamber. But so is this. The difference is this is portable. Now you're telling me, well, wait a minute, this one reads an MR per hour and this one reads in millicuries. Of course it does. Because every isotope has a gamma constant that is based on its energy and how it decays. And it converts ionizations in air to activity. And that's what happens when you push that button on the dose calibrator and say, oh, this is I-123. And that's why it's inaccurate if you push the wrong button. Because I-123 is going to decay differently than technetium-99m. So how does this ultimately work? Your gas is in here. Photon comes in, hits the gas molecule, electron comes out, gas becomes positive, ion pair. Electrons are captured at the anode, voltage is applied. High voltage down here, number of ion pairs collected here. GM meter, we talked about this yesterday, much higher voltage, very sensitive, picks up small amounts of radiation. Ionization chamber, which is both your portable ionization chamber and the dose calibrator, lower voltage, higher activity, much more accurate. All right, how do we know this thing's working? And NRC inspectors love to do this. They love to walk in and they're like, okay, I see that you used this GM meter yesterday. You did a survey of the department. How do you know it's working? And you have to do 3 things. You have to check if you have a dedicated source, which it's not required to have a dedicated source. If you have a dedicated source, you're going to put your probe against the source, make sure you get a reading. If you don't have a dedicated source, you just find a known source of activity, put it next to the activity, make sure you get a reading. That's number 1. 2, battery check. And if you fumble around, you don't know how to check the battery, then they're going to assume that you don't actually do the daily check. And 3, make sure it's not expired. Make sure it's been calibrated within the last year. Those are the 3 things you need to do. Now, annual calibration, that's done with the cesium-137 source, very high activity. We don't keep these in our department, that's why we have to send it away. And that's a calibration. Whenever you're thinking about instrumentation and quality control, always think, is this a check to see if it's working, or if it's a calibration where I'm doing something to make it work? There's 2 different types of quality control. All right, ionization chambers, dose calibrator, portable ionization chamber. Make sure you know your 4 quality control tests. Accuracy, we're going to do once a year. Accuracy begins with A, so does annually. That's just what it is. How close is it to the true reading? Constancy is precision. I know today in our departments we're doing daily accuracy instead of a true precision test, which is okay. But on your board exam, constancy is a test of precision. Are my readings today the same as they were yesterday and last week? Are they precise? Are they the same? Geometry. It's the only class I failed in high school was geometry. It was awful. I just could not conceptualize all the different shapes. But geometry is about shapes. It's about if I change the shape or the size of the radiation, is it going to still read accurately? So we're going to change the shape. How are we going to do it? We're going to add saline and make it bigger. And then linearity, is it accurate over a wide range of activities? We're going to put 200 millicuries in there, 100 millicuries, 50 millicuries, 10 millicuries, 100 microcuries. Can it read all those different ranges? Now the good news is, all 4 tests, you do a percent error. All 4 tests have the same pass rate, 10%, plus or minus 10%. Now if accuracy or constancy fails, we send it for repairs, and if linearity or geometry fails, we do a correction factor. How do we do percent error? Expected minus actual divided by expected. Expected is what you calculate. You'll always calculate something for your expected reading. Actual is what you get when you put it in the dose calibrator. All right, for an accuracy and a constancy, there's 3 sources we can use. Those are the half-lives, those are the energies. Go ahead and take a picture of that, make sure you know those. Let's do an example. We have an expected reading of 78.5 and an actual reading of 70.1. What is our percent error? We're going to take our expected 78.5 minus our actual 70.1 and divide that by our expected 78.5, times that by 100. In this case, it comes out to 10.7%. Over 10%, we cannot use this dose calibrator. We have to send it off for repairs. All right, geometry. Again, this is all about if we change the shape, is it going to change the reading? So we do that by adding saline to change the size. So I have all of my different volumes. This was my expected reading. And all I did was change the different volumes. I'm going to do expected minus actual divided by expected to get my percent error. If it's over 10%, it fails. So what do we do if it's over 10%? Fun fact, new dose calibrators do not fail geometry. They just don't, okay? So eventually we're probably not going to be doing this test anymore because they do not fail geometry. But if you have a really old dose calibrator, it might. So if it fails, we're going to do a correction factor. Now, if you get a question like this on your exam, step 1 is first make sure it fails. Okay, if it asks you to calculate a correction factor, make sure it fails first. So if my expected reading was 2.95 and my actual was 2.45, my percent error was 17%. It failed. So I have to do a correction factor. Correction factor is expected over actual In this case, it comes out to 1.12. 1.2. What do I do with correction factors? Factor means multiply, so I'm going to multiply it. All right, and then finally linearity. Linearity is all about, does it read accurately over a wide range of activities? So I'm going to start with the highest dose that I use in my department. I can use technetium. If I'm in PED, I can use F18, much faster. Measure it 2 to 3 times per day. Make sure you document your activity, your background, and the date and time. Expected activity is based on decay. If you have a syringe of technetium, you can calculate at any given time how much is in that syringe as it decays, as long as you don't take anything out of it. Calculate the percent error, graphed on semi-log paper. All right, so this is what it looks like. Here are all our percent errors. Now, what is semi-log paper? Semi-log paper means that on one axis, it's linear. So on my time, it's linear. All the boxes are the same size. But on the y-axis, which is activity, everything is separated by a power of 10, which is a logarithmic scale. That's why it's semi-log. One axis is logarithmic, the other axis is not. And when I log this on semi-log paper, my line becomes straight. Now, if my y-axis was also linear, then I would get what's called an exponential curve, because decay is exponential. But you make this axis logarithmic, it becomes straight. All right, now what the heck is this? This is if you're working for an employer that likes you. They will invest in you, and they will buy you a Kelly check system. These are attenuation sleeves. This is another way of doing a linearity without spending 4 days to do a linearity. So we can do a linearity in 15 minutes. All right, again, only if your employer really likes you will you get this. So what do? We're going to use shielding instead of time, instead of decay. This one is plastic. You put your syringe down in there and you put that in the dose calibrator. And then each one of these shields represent attenuation, and so it's going to lower the amount of activity. It gives us that full range of different activities. All right, those are gas field detectors. We also have some scintillators. We like our well counter for doing wipe tests, although the NRC says you can use an uncollimated gamma camera or a GM meter, but we like the well counter because it has a high efficiency. Why does it have a high efficiency? Because that crystal surrounds it. You've got the PM tube behind it, just like a gamma camera, but all it's going to be doing is counting. All right, we have to do a constancy on the well counter. It should be plus or minus 10%. I'm going to skip that and move into our gamma cameras. A lot of things that we need to know with our gamma cameras. When the radiation leaves the patient, first thing it encounters is the collimator. We all know that. But one thing I think we don't think about so much is when that photon hits the crystal and turns into a light photon, it doesn't just keep going straight. Look, it scatters, okay, and hits multiple PM tubes. And that's important because when it does that, all the PM tubes are talking to each other to determine the exact location of where the dot goes in the screen. That's what determines your X and Y position. All right, low, medium, high energy. That's going to determine the type of collimator. Now, the reason we don't like low or high and medium energy photons, I mean, we learned that all through school. It's like, oh, our cameras don't like high and medium energy. We like low energy. That's the sweet spot, right? It's not because of the crystal. It's because of the collimator. You know, the collimator seems like the most simplistic thing, but we can't get past the collimator when it comes to our medium and high energy. And the reason is, medium and high energy, you have to have thicker septa to stop the photons that are coming in at an angle. And since you have to have thicker septa, you have to have fewer holes. Fewer holes reduces the sensitivity. If you have fewer holes, you have to make the holes bigger. And we know that bigger holes reduces resolution. So automatically we have a reduction in sensitivity and resolution simply because the collimator can't handle medium and high energy photons. All right, Now with our parallel hole collimators, there's always a trade-off between sensitivity and resolution. You increase sensitivity, you decrease resolution. Increase resolution, decrease sensitivity. It's always a trade-off, okay? Except in one case. And I always say I can walk into any nuclear medicine department and in 10 seconds I can tell if that technologist is a good technologist or a bad technologist. And the way I do that is I look at how close the camera is to the patient. Because that's the only instance where we don't have a trade-off of sensitivity and resolution. You bring the camera closer, you increase resolution. Sensitivity stays the same. Sensitivity stays the same. All right, PM tubes, we know about that. Difference between emission and transmission. Transmission means the X-ray tube or the source. Doesn't need to be an X-ray tube. You can use a cobalt-2 source to do a transmission scan on a patient for a sentinel lymph node. It's just the source of radiation is outside of the patient and it's transmitting through the patient and being picked up by detectors on the other end. Whereas emission, the patient is radioactive and emitting the source and it's being picked up by radiation detectors. All right, let's talk about the sonogram because nobody understands sonograms. And I didn't understand sonograms until I've been teaching for several years because I don't think sonograms make any sense at all. Well, until I figured it out. Why do we do a sonogram? We're looking for motion. Okay, we're looking for motion. But let's talk for a second how it is actually made. And I think it's most simplistic if you look at a point source. So we have a point source here, and we're going to do a SPECT acquisition because sonograms are for SPECT. And we have our camera projection here. It's looking at our point source and all of the activities on the left side of the camera. Now, as the camera moves around, now all the activity is in the middle of the camera. And as it keeps moving around, now all the activity is on the right side of the camera. So I'm going to take this projection where the activity is all the way on the left side, and that's where it goes, on the left side. I'm going to take this one where it's in the middle, it goes in the middle. This one is all the way on the right side. So all I'm doing is adding each projection up together and forming an image to see if my patient moved. All I'm doing. All right, a couple phantoms here. This is Cobalt 57. This is our flood that we do. These are our resolution, spatial resolution testing. What you might not remember is this also tests linearity because we're looking to see if those lines are straight. Linear means line. Flood, 5 to 15 million counts. You can do it intrinsically or extrinsically. You know, when I was first a technologist and we did daily floods, we'd print it off on film, we'd look at it, hold it to a light, look at it, and be like, yep, looks good. Now we can actually quantify it. And what we're quantifying is how close are all the pixels to each other. If you put a uniform source of activity and every single pixel is getting the same amount of activity, they should all be counting the same amount. And so you want to find out what is the maximum count and the minimum count and how much is difference between them. So that's ultimately what you're looking for, is how far apart are the counts. So your uniformity calculation is max minus min over max plus min. All right, JZAC Phantom does three things: uniformity, contrast, resolution. SPECT Phantom. All right, PET's a completely different beast. And if you stop and think about it, SPECT stands for single photon. One photon. PET is two photons. So how we acquire is going to be completely different. With SPECT, single photon. If it comes in straight, it's counted. Comes in an angle, it's not counted. PET has two photons, and they're going to hit opposite detectors. And when they hit opposite detectors, it has to pass two tests. First test is the timing test. Did they hit it at the same time? The second test is the energy test. Were they the same amount of energy? All right, these are all the different positron emitters that you need to know. These are all the different energies, and based on the energy determines the range. Why is that important? Because the further that positron travels before annihilation, the more error that is introduced to your image. So rubidium It goes 1.7 millimeters before it annihilates in every direction, which means every line of response has 1.7 millimeters of error in it. Compare that to F-18, 0.3 millimeters. Significantly different. So, and also, some are made by a cyclotron, some are made by a generator. Make sure you know all the half-lives too. All right, 3 possible coincidences. First one is what we want. Goes off in opposite directions, hits opposite detectors, passes the timing test and the energy test. On the right side, goes off in opposite directions, but this one scatters before it hits opposite detectors, passes the first test of timing, fails the energy test. Not gonna count it. And then this one, this is the only one that has 2 annihilations. And by the way, everything has 3 names. So this can be called accidental, random, or false. I think we really should think about starting a petition for a consensus conference on terminology where we can all come together and decide what we're going to call this. Because it could say accidental, it could say random, or it could say false. And there may even be another term that I'm not aware of. But what happens here? We have 2 annihilation reactions. This detector and this detector hit at the same time and the same energy, but they're from two different annihilation reactions. It's going to be counted. There's nothing you can do about that. Now you can lower the probability of it happening by lowering the amount of activity. You get more activity, that's going to happen more often. So it's kind of interesting because like in our spec, you get more activity, you get more counts, we like that. You get a better image. Don't have to image as long. Of course, you're radiating the patient more, but with PET, you actually degrade the image by giving more activity because you have accidental randoms or falses. All right, 2D versus 3D simply means we have a collimator. What do we know about collimators? It's going to lower our sensitivity. Lower sensitivity, lower counts. We have to give more activity. The 3D, no collimation, higher count rate, higher probability of false, random, and accidentals. So when we switch over to 3D, we have to lower our activity. All right, not going to talk about the X-ray tube today. I know that disappoints everybody. Everybody likes the X-ray tube. But we are going to move in. Actually, I'm going to talk about just one thing. Because I think this is the easiest one. MA versus KVP. All you have to do is think about what you already know. If I ask you how much radioactivity did you give that patient, short for radioactivity is activity. I'm asking you how many millicuries. That tells me how much. MA also starts with an M, millicuries MA. That's how much radiation did you get, how many x-rays. Whereas KVP, that's the energy, just like KEV, KVP. So energy is KVP. And the reason it's not KEV is because x-rays are polyenergetic. And gamma rays are monoenergetic, one energy. So we can quote that energy, and we love doing that, at 140 keV. Whereas with x-rays, like, well, here's the whole range. I'll give you the maximum, but here's the whole range. All right, which brings us to radiation safety. What do you need to know about radiation safety? You need to memorize a lot of stuff. But I'll tell you what, once you pass your board exam, you get to forget it like the rest of us. In fact, a lot of this stuff I don't have memorized. If I didn't have it in front of me, I would forget it. But make sure you know it for your board exam. All right, 3 CFR regulations, 19, 20, 35. I don't think you're going to get a question about 19. It's just that notice to employees and inspections. 20, radiation protection. If the question is about radiation protection, say it's 20. If it's about your radioactive materials license, it's 35. Make sure you know your signs. The difference between radiation area and high radiation area is that number right there. The rest of it's the same. Radiation safety education required for anyone receiving 100 milligram. 100 milligram is important because that's what triggers you no longer being a member of the public. You can only get 100 milligram a year if you're a member of the public. But once you're over that, you're no longer a member of the public. And if you're working as a radiation worker, you have to get radiation safety education that is specific to your license. That means, and you can give the radiation education to each other. It's not like you have to pay a physicist to come in and do this, but it has to be specific to your license. It's like once a year you sit down, it's like, okay, everybody, here's how we check in a package. Here's how we do our surveys at the end of the day. Here's how we convert CPMs to DPMs in our department. Here's our action limits. Here's how in our department we clean up a spill. So it has to be specific to what you're doing. All right, restricted versus unrestricted areas. Making a room restricted is simply just putting up a sign that says caution radioactive materials. Now it's restricted because it has a sign warning people. If there are no signs, it's unrestricted. Public hallways, waiting rooms, unrestricted. These are the two things you need to know. You have radiation in your department that could be received by members of the public. So you are responsible for that radiation. And you're only responsible when it's not in the patient. Once it's in the patient, it's like you're not responsible anymore. It's the weirdest thing. So I can inject 30 millicuries of sestimivir into my patient and say, go sit in that waiting room and irradiate everybody in that waiting room, in that unrestricted area. But I can't take that same syringe of 30 millicuries and put it in the waiting room. All right, so does not include patients, but otherwise, I have to make sure no member of the public receives more than 2 milligram in any hour, which is not 2 mR per hour. It's a total of 2 milligram in an hour, or 100 milligram in a year. All right, leak testing. It's a glorified wipe test. That's all it is. It's a wipe test on our sealed sources, and we call it leak testing. All we're going to do is we're going to do a wipe of our leak, of our sealed source, put it in a well counter, and see how much activity is there. The regs say 0.005 microcuries. That's the maximum that can be removed. And you're thinking, Sybil, wait a minute. When I put something in the well counter, it doesn't give me microcuries. That's the dose calibrator. And the dose calibrator is not going to read down to 0.005 microcuries. So how do I do this? Well, you're going to put it in the well counter, and it's going to give you CPM. You're going to divide by the efficiency, and that's going to give you DPM. And then you're going to convert DPM to microcuries. And if it's less than 0.005, it passes. If it's more than 0.005, do it again. Because you don't want this to fail. Trust me. You don't want this to fail, because if it fails, you have to assume that this has been leaking for the last 6 months. Anybody that's been in contact with that source, you gotta check them for contamination. You gotta check your department. You gotta check everywhere. And not only that, you gotta take that out of service. So if you rely on that source for your department, now your department's closed. So all kinds of things happen if it fails. Now at the same time, do a sealed source inventory. What does that mean? Well, if you've ever worked in retail, you know what inventory is. It's a bad day, right? Nobody likes doing inventory. But it's simply, what do you have? How much do you have? And where is it? All right, we're gonna do the same thing. What do you have? I've got a Cobalt 57 sheet source. Where is it? It's in the closet in a lead line container. How much do you have? I've got 8.5 millicuries. That's all it is, but make sure you do it every 6 months. All right, 4 ways we can get rid of our waste disposal. If you decay it in storage, make sure it's less than 120 day half-life. You know, one time I went into a department and they had like 3 cobalt sheet sources sitting in the closet. And cobalt has a half-life of 271 days, okay? And I'm like, why do you guys have those sheet sources in your closet? And they're like, well, we're decaying them in storage. And I'm like, well, you can't. The half-life's more than 120 days. And they knew I was an educator. And they're like, oh, well, do you want one? I'm like, no, that's not how any of this works. You can't do that. You can't just give me a cobalt sheet source. You have to get rid of that. You have to send it away to an authorized recipient. Right here, authorized recipient. And it's expensive. It's not cheap to do that. So usually when you buy your sources, they send you a return kit at the same time. It's like, you can't buy it unless you also pay to have it sent back. All right, surveys. It's It's not gonna say daily survey, weekly, like on your board exam. It's gonna say ambient dose rate survey, 'cause we're fancy now. And it's gonna say removable contamination survey. That's what it's gonna say. So make sure you familiarize yourself. And now you're not gonna say that in clinic. You're like, have you done the ambient dose survey today? You're not gonna say that. But that's what it is on your exam. All right, how often do we have to do it? On a reasonable schedule. Whatever your license says you have to do it. Okay, so it might be different depending on where you work. You're also required to monitor your hands and feet every time you leave the department. I'm sure all of you are doing that, right? You leave the department to go get a patient, you're gonna monitor your hands and feet. But when the inspector comes in, you are. And on your board exam, you are. All right, minor spills versus major spills. There's no like set, like, hey, this is the minor spill versus the major spill. You'll have that established for your own department, but the NRC doesn't basically say that. Rule of thumb, over 100 millicuries of a diagnostic makes it a major, and any therapy is a major spill. So make sure you know what to do with those. All right, required postings. I think we talked about this yesterday, Form 3. This is what Form 3 looks like. Make sure that's posted in your department. Your license should also be posted, not in your license, but the hospital's radioactive materials license. You know, I think sometimes Joint Commission requires you to have your license posted, but the NRC does not. The NRC really doesn't care if you're credentialed, educated, they don't care. All right, they're licensing the hospital and they're authorizing the physicians and they're delegating authority to the radiation safety officer, but they really don't care about you. I care about you, but the NRC doesn't. So your license is not going to be up there, but the radioactive materials license will be. All right, we talked about Form 4, Form 5, radioactive materials packages, Type A accepted packages. When you send it back, that's a Type B, by the way. You're never going to see one of those. Generators come in Type A packages, not Type B. I know that's a misconception. So when we return the material, we flip the card, it becomes an accepted package of limited quantity. Make sure you know all your labels. And did you ever notice that on yellow 2 and yellow 3, it has this rectangle here? That's for the transport index, and there's no rectangle on white 1. There's no transport index for white 1. And the reason is if you are transporting a white 1 package, you as the transporter shouldn't be getting any more radiation in the background because there is no transport index. All right, you know all these things. All right, let's talk briefly about our exposure. So there's some terms that we need to know. We need to know deep dose equivalent and committed effective dose equivalent. Both of these are exposure to our internal organs, okay? And the difference is the deep dose is from external sources, committed dose is from internal sources. So the only way you're going to get a committed dose is if you ingest, inhale, or absorb radioactive material. It gets into your body. And if it gets into your body, then you're going to do a bioassay. And the physicist is going to calculate how much you were exposed to. So hopefully you don't get a committed dose, okay? Hopefully your coworkers like you enough that they're not going to inject F-18 into your coffee. That would be awful. I've never heard of that happening, by the way. But if you do get a committed dose, that's going to be calculated. Now, your deep dose and your committed dose, you add that together, that's your total effective dose equivalent. That's what you see on your badge reports. The shallow dose, that's your extremity badge, but it can also be extrapolated from your whole body badge. And then the lens of the eye dose, again, it can be extrapolated from the whole body badge, or they actually have a lens badge that you wear on your eyeglasses, like on the corner of your eyeglasses. Make sure you know all your exposure limits. 5 rem for whole body, lens of the eye is 15, extremities, 50. Think of your extremities as an organ because it's all 50. Public, again, that's that 100 millirem. These are not members of the public. The fetus is currently residing in an occupationally exposed worker, so they get 500. Anyone under the age of 18, 500, and family member of a therapy patient, 500. All right, linear energy transfer. I think we talked about this a little bit yesterday as well. Always know what the terms mean. You know, instead of memorizing what this is, think linear, that's line. Lines can be measured in micrometers. energy, KeV, how much energy is deposited per unit length. And I think we talked about that as well, so we'll skip that. And that brings us to radiopharmacy. So we're going to do 30 minutes of radiopharmacy, and that's going to take us to our first break. So, sources of radioactivity. There's two sources. Naturally occurring. There's a lot of stuff in nature that is radioactive. You can go find radioactive rocks if you want to. They're out there. Or you can buy them on Amazon if you really want radioactive rocks. They are out there. Artificially produced is what we use for nuclear medicine. All of ours are artificially produced. We don't make any. How do we make them? 3 ways. I would argue 2 ways, because I don't think generator is an actual production method, but nobody asked me. But the reactor, the accelerator. In its easiest form, a reactor, we're adding a neutron, an accelerator, we're adding a proton. And if we add a neutron, we know a neutron turns into a proton. To balance that out, we need a beta negative particle. Proton turns into a neutron. To balance that out, we need a beta positive particle. Also, the alternative, electron capture. So if it's made in a reactor, beta negative. If it's made in an accelerator, beta positive or electron capture. Okay, so when we make these isotopes, they're going to undergo what we call nuclear transformation. Transmutation is where you actually have an element change. It changes from molybdenum to technetium. It changes from fluorine to oxygen. The element changes. That's transmutation. Alpha, beta negative, beta positive, electron capture, all transmutation. De-excitation, no element change. That's where you have gamma emission and internal conversion. Remember, your teenager slamming the door on her way out, hitting your own electron on your way out. That's internal conversion. Okay, so let's talk about the nuclear force. It's my favorite subject. So how we read this chart is, this x-axis is the distance between positive charges. Positive charges we're talking about is the proton and the positively charged nucleus. Or just a simple magnet. We've all done this. You have the 2 positive ends of a magnet. You try and bring them close together, and all of a sudden they start going back and forth like this because you can't bring them together. So as you bring them closer together, the repulsion increases until you're able to get them so close together, Coulomb force breaks down, nuclear force takes over, and you have strong attraction. And the nuclear force is the strongest force in nature. Those protons and neutrons being held together in the nucleus is the strongest force in nature. So, how does cyclotrons work? Because we have to add a proton. We have 2 Ds. Called Ds because they're shaped like Ds. And in the middle is your particle source. And it's going to be a proton and 2 electrons. Net negative 1 charge. So it's a negative ion accelerator. One side of the Ds are going to be positive, the other side's going to be negative, and they're going to switch back and forth really fast. And as they do that, this particle is going to go around in circles, being attracted and repelled until it gains enough kinetic energy to slam into the target. So it can get really, really close, overcoming the Coulomb force, allowing nuclear force to take over, and then the target becomes the product. Cyclotrons are characterized by the energy that's given to the particle that's accelerated, that proton. The more energy, the more different isotopes that can be made. All right, so what does this look like? Whenever we write this out, in the middle, where you have your parentheses, in the middle, the first is what goes in, so a proton's going in. The second is what comes out. A neutron is coming out. So I can look at this, and I can say, if a proton goes in and a neutron comes out, I start with O18, 18 is going to stay the same. That's not going to change. My protons, if I start with a target that has 8 protons, and I'm adding a proton, now it becomes 9. Since I changed the number of protons, I've changed the element, and that's transmutation. So, with cyclotrons, we're adding a proton, we have to speed that proton up. The opposite is true for reactors. Reactors, we're adding a neutron, we have to slow it down. And when we slow it down, we call that a thermal neutron. I don't know why. I probably need to look that up. Because I always say I don't know why. But a thermal neutron is a neutron that's been slowed down. Because the neutron's neutral. It's not going to be, there's no repulsion because it's neutral. So if you don't slow it down, it's going to go right through the nucleus. You have to slow it down. It's kind of like, you have to make it so it comes to a stop right when it hits the nucleus. And so this is uranium-235. The neutron is going to go into the uranium-235. And the first thing that happens is it elongates. Remember what happens when we introduce distance? The nuclear force relies on everything being really close together. When you add that neutron, now we have distance. Distance. Nuclear force breaks down, Coulomb force takes over, and it splits apart because they repel each other. Splits apart. So these are our fission products. What are they? Moly-99, I-131, cesium-137, xenon-133, all of the beta-negative emitters. But then there's extra neutrons that go on and continue this process. All right, so there's two types of reactors. There's fission, and then there's neutron activation, or neutron capture. Both are going to use thermal neutrons, okay? But this is more like the cyclotron, where you have what comes in and what comes out. And almost always, it's going to be neutron in, gamma ray out. So if we think about that, there's no protons changing here. So my element stays the same. The element only changes when you change the number of protons. But my number of neutrons are changing. So lutetium-176 becomes lutetium-177. Samarium-152 becomes samarium-153. And I promised yesterday I would talk about this. We're going to talk about moly being made with neutron activation. We don't necessarily like that, but we can. If you take moly-98, add a neutron, it becomes moly-99. And we did that for a while with those North Star generators. I'm not sure if we're still using those, but we did that for a while. It worked, but it had a low yield. You couldn't get as much as what you get with fission. And the other problem is that it's something called specific activity. This is not radionuclidic purity. People get those mixed up. Specific activity is how much do you have of the element, that the isotope of that element that you want, which is moly-99, over how much do you have of all of the isotopes of that element. So we've got some moly-98 that's going to be in there. So that lowers the specific activity. All right, finally, generators. Generators, I don't consider them a production method, but on your board exam it is. The parent is put in a generator. The parent is made by a cyclotron or a reactor. So the parent is produced by one of those methods. The parent goes in the generator. The generator doesn't make noise. You don't plug it in. There's no power to it. I kind of wish they'd call it something different than a generator, but again, nobody asked me. But it's called a generator. And what's happening is the parent that's made in one of these other methods, we're simply waiting for it to decay into the daughter. So the Molytech generator, here is the parent decaying, which is the moly. And then the daughter, of course, is increasing, and then it starts decreasing at the same rate as the parent. All right, inside the generator. This is the inside. Here's the column. Here's it blown up. The column is made of alumina. Alumina forms a chemical bond with molybdenum. As the molybdenum decays, it undergoes transmutation, which means that the symbol changes, so it's not going to have the same chemical properties as the parent. Falls off the column. And all we have to do is take saline, run it over the column, and we get our technetium. Easy peasy. All right, we talked about that yesterday. three types of QC on the generator: radionuclidic purity, radiochemical purity, and chemical purity. Radionuclidic purity, what radionuclide could be in our eluate that we don't want? Moly. Radiochemical purity, we're going to do this on our kits. What could be there we don't want? Hydrolyzed reduce and free tech. And then chemical, there's no radiation here. The only chemical we're concerned about is aluminum. So, radionuclidic purity testing. How do we do this? We're checking to see if there's a radionuclide that we don't want. In this case, molybdenum and our technetium. We're going to take advantage of molybdenum having higher energy than our technetium. And so we're going to put our vial that we got from our generator in this lead shield. We call it a moly shield, but don't be confused. It doesn't shield the moly, it shields the technetium. So we're going to put it in the moly shield. We're going to put the lid on the top. We're going to take this whole thing and throw it in the dose calibrator. And when we do that, it tells us how much moly we have. And then we take it out of the shield, we measure it again, and that tells us how much technetium we have. This is what we're allowed: 0.15 microcuries of moly per millicurie of technetium. So, microcuries of moly go in the numerator, millicuries of technetium in the denominator. That's going to give us our ratio. Over time, that ratio changes. The reason it changes is because technetium is decaying at a much faster rate than moly is. So, this is going to be going down very quickly, and as that goes down, the ratio goes up. Whatever happens to the denominator, the opposite happens to your answer. So 0.15 microcuries of moly per millicurie of patient. This is at the time of administration. So we need to know how long before that ratio hits 0.15. If it's more than 12 hours, our expiration is 12 hours. If it's less than 12 hours, then that's the expiration time. Let's do a couple problems. What is the concentration of moly in a vial containing 300 millicuries of tech and 18 microcuries of moly? We're going to take our 18 microcuries of moly and put that over our 300 millicuries of technetium. Do not change the units. That's going to give us 0.06, and our unit is microcuries of moly per millicurie of tech. So right now it passes. All right, let's look at it a different way. A vial of generator eluate has 756 millicuries of technetium. What is the maximum amount of molybdenum that we're allowed? So I'm going to start with what I'm given, 756 millicuries of technetium. This is going to be a conversion problem, and my conversion in this case is 0.15 microcuries of moly equals 1 millicurie of technetium. So I started out with 756 millicuries of technetium. Whatever's on top goes on bottom. Millicuries of technetium. Put my microcuries of moly in the numerator. I put in my numbers. That cancels. And you're probably thinking, I know how to do that. Why is she writing that out? I just want to show you that conversions work, and what you know in your head, you can actually write it out, and it's the exact same thing. So when you come upon a problem that you don't understand and can't do it in your head, you know how to write it out. All right, so my answer here is 113.4 microcuries of moly. Now, how long is it good for? Our lovely equation here tells us, this gives us hours. That tells us how many hours before it hits 0.15 microcuries of moly per millicurie of tech. So let's do a problem. Let's look back at our 0.06. So at 0800, we have 0.06 microcuries of moly per millicurie of tech. What is the expiration time? What we're going to do is T equals negative ln 0.06 over 0.1052 minus 18.03. We're going to put that in our calculators, and when you do, don't make this mistake of hitting the second ln. We're so used to hitting second ln when we decay, but this one is just the ln. All right, when you do that, you come up with 8.7 hours. radiochemical testing. Radiochemical testing, we're looking for hydrolyzed reduce and free tech. You can actually do the hydrolyzed reduce before you make your kit, because the hydrolyzed reduce is a characteristic of the technetium, whereas the free tech is a characteristic of, is there any technetium that didn't bind to the ligand? So, I always wonder, it's like, how come we do a one strip test, and sometimes we do a two strip test? So you can check for hydrolyzed reduced on your eluate, and then you only have to do one strip test on all of your other of your kits. All right, so how are we actually doing this? We're going to take a strip of paper. It's either going to be Whatman paper or silica gel. When I was in school, we had to know all of the different papers for all of the different radiochemical purities. We had to know which solvents went with each one. We had to know all of the passing results. And maybe you still need to know that. I don't know. But I remember I had to learn all of that stuff. And then, of course, I forgot it after I took the exam. But we're not making kits as much as we used to. So it's not that as important for us to know these things anymore. Okay, so we're going to take a piece of paper, Whatman paper or silica gel. We're going to put in a solvent. It's either going to be saline or acetone. Acetone is nothing more than fingernail polish remover. And we're going to put our eluate at the bottom. We're going to let the solvent go up. And as it goes up, it separates the components, and then we're going to count each one. As a rule, free tech always flies to the top because it's free to fly away. Hydrolyzed reduce stays at the bottom because it's heavy. All right, we're going to go through one problem here. We have a hydrolyzed reduce on the left. We have free tech on the right. With hydrolyzed reduce, it's at the bottom. And our tech MDP is at the top. On the right, free tech is at the top. And our tech MDP is at the bottom. So in this example, the author was nice enough to add the total counts for us in each one of these strips, which is nice. It makes it so much easier for us. And that's where we always make the mistake, is we forget to add it in our denominator. All right, we're going to do the hydrolyzed reduce first. Whatever you want to find the percentage of, that's what goes in the numerator. So I'm going to take my 2,530, divide that by my total counts, 90,530, times that by 100. Percent hydrolyzed reduce here is 2.8%. And on the right side, I'm going to do my free tech. Got to find the percentage of free tech. So what I'm going to do, I'm going to take those top counts this time, 1,049, divided by the total counts, 90,599, times that by 100. My percent free tech is 1.2%. And now before I do anything else, I'm going to go back and look at the problem, and I'm going to find out, do they want to know the percent radiochemical impurity or the percent radiochemical purity? Because if it's impurity, I'm just going to add these two together, and my answer is 4% impurity. But if they want to know the purity, I'm going to take 100 minus 4, and my answer is 96%. And it might say, what is the percentage of tech MDP? Because that's the purity, 96%. All right, and then finally, chemical purity test. This is where we're looking to see if there's alumina in your dose. So we're going to take the pink paper. We're going to put the standard on it. The standard has 10 micrograms per ml. And then we're going to put our sample. Here's the standard. Turn pink. Here's our sample. It's kind of hard to see. Did not turn pink, so it passed. All right, I think we did a couple of these yesterday, the theoretical yield, but we'll do another one. So, the theoretical yield is looking at, you have your generator. I want to know how much is in that generator, how much technetium is in that generator. And we can calculate that at any given time because we know the moly is decaying at a steady rate, and we can always calculate how much moly we have because the moly never leaves. The only thing it's leaving is the technetium. The technetium is going to be increasing, and then at some point it starts decreasing at the same rate. So, at any given point, we can calculate the moly, and if we're given the ratio between the moly and the tech, we can calculate the amount of technetium. So here we have a problem that a moly tech generator has 5,200 millicuries at calibration, so eluted 20 hours later, and we're given the fraction. So we're given the 20-hour fraction, so we're right here at 20 hours, and this fraction of moly to technetium is 0.83. That means I have 0.83 millicuries of technetium for every millicurie of moly. So the first thing I'm going to do is I'm going to decay my moly, because I have to find out how much this is. So I'll take my 5,200 e to the negative 0.693 divided by 67 or 66, depending on what book you're reading, times 20. So my activity is going to be 4,222 millicuries of moly. I know this. Now I have to figure out this. All I have to do is multiply it by the fraction. And my answer is 3,505 millicuries of technetium. That is my theoretical yield. Now the actual yield is taking the theoretical yield and multiplying it by the elution efficiency. What percentage can I get out of that generator? So if I have a theoretical yield of 750 millicuries and an efficiency of 92%, all I have to do is take my 750 millicuries, multiply that by 0.92. I'm not going to divide it by 0.92 because I can only get 92% out. So I know that my answer is going to be less than 750. Comes out to 690 millicuries. All right, we can look at it the other way as well. You have a Molytech generator with a theoretical yield of 550 millicuries, but you only got 475 in your elution. What is the efficiency? Well, that goes back to the efficiency of the well counter. If I have a bowl of 100 M&Ms and I ask you to count it and you only count 95, that's 95% efficient. So I'm only getting 475, but there are 550 there, times that by 100, I end up with 86% efficiency. All right, now we can put it all together. We're going to do one last problem, and then it is break time. And I believe we are exactly on schedule. All right, I have a generator. It has 4,000 millicuries of molybdenum in the column at 0800. I want to know how much can be eluted 6 hours later at 1400. My elution efficiency is 92%, and my 6-hour ratio is 0.441. So again, here's my moly decaying. Here's my technetium increasing. But now I'm all the way down here at 6 hours. And so my ratio is going to be significantly different, 0.441. My ratio at 20 hours was 0.83 because it was all the way, more time had elapsed. Step one, find how much moly I have. A sub T equals 4,000. E to negative 0.693 divided by the half-life. Could be 66, could be 67 hours, depending on the book you're reading. I'm going to use 66.7. That's the book I'm reading. Again, we need a consensus conference. Start a petition. Times, how much time has elapsed? 6. Now my activity is 3,758 millicuries of molybdenum. I found this. Now I need to find this. I have to multiply by my ratio. This gives me my theoretical yield, which comes out to 1,657 millicuries of technetium, theoretical yield. But it's asking for my actual yield because I have a 92% efficiency. Answer comes out to 1,524 millicuries of technetium that you're going to elute from the generator. All right, that was a lot. We've gotten through all the science stuff. When we come back, we're going to do clinical procedures, followed by a rapid fire math session. We're going to do a rapid fire math session, and then we'll end with a Kahoot game. So we're going to do a full 15-minute break. Go fill your coffee mugs, and I'll see you in 15 minutes.